Let's do an example of sketching the transformation of a tangent function. This will feel very similar to sketching transformations of other trigonometric functions, sine of t and cosine t, but there will be some differences. However, we will follow the steps where we transform those important x coordinates, or again, t coordinates here, of minus pi over 2, minus pi over 4, 0, pi over 4, and pi over 2, and also transforming the midline and the upper and lower lines here that we have. So the first thing that we'll do is we'll identify the parent, which of course is tangent of t. I'm going to rewrite my graph in terms of the parent, negative f of 2/3 t plus 1. And I'm going to find my midline, my upper line, and my lower line. I suppose I still need to list the vertical transformations in order to do this. So we have a vertical reflection about the x-axis, and we have a vertical shift up by 1. So when I go to compute my midline, that's going to be my old midline, which has a y value of 0. We multiply by -1 to reflect about the x-axis, and then we shift up by 1 to get a new midline of y equals 1. So y equals 1 is going to be our new midline. Let's compute our upper and lower lines. So upper / lower. So we'll take 1 and -1, and we'll apply our transformations, that is reflecting by multiplying a -1 and then adding 1. So the lower line here is going to be 0, and the upper line is going to be, I multiply by -1 to do my reflection, then add 1, and I get 2. So I have my upper and lower lines here, and now I'm going to include those on a graph. So I have my ty axis here, and I'm going to create a scaling. Let's make this 1. That would make this 2, and so my mid, upper, and lower lines will look something like this. And this will help me when I go to plot my y coordinates for the x coordinates that I'm about to list. Now, a brief remark. Remember, for this particular problem, we have this vertical reflection here. So when I go to sketch my graph, usually we do the lower, the midline, then the upper line. But in this case, what we're going to do is we're going to start at the upper because the graph is reflected. Then we'll go to the mid, then we'll go to the lower. Much like what we did when we graphed sine and cosine. But we'll see that in a minute. Now let's do the second step, where we will find the important t-coordinates, just like we did with sine and cosine. Of course, there will be a slight difference here because with sine and cosine, we transformed 0 into pi, and then we found the rest of the important t-coordinates by taking averages. And while we will do the averages part, the points that we're going to transform first are minus pi over 2 and pi over 2. So those will be our first and our fifth important t-coordinates, and the transformations of those will determine where the asymptotes are located. Then we'll find our third important t-coordinate and our second and fourth by taking averages. So before we do that, we need to identify the horizontal transformations that are going on in our problem. And here we have a horizontal stretch by 1 over 2/3, which is 3/2. So in order to get our first important t-coordinate where one asymptote will be located, we're going to take the minus pi over 2, the first important t-coordinate of the parent function, tangent of t, and then we're going to multiply it by the horizontal stretch, 3/2, and that's going to get us minus 3 pi over 4. The second important, the last important t-coordinate will be obtained by taking pi over 2 and multiplying that by 3/2, and that will get us 3 pi over 4. So we can go ahead and mark that in. This important t-coordinate here is negative 3 pi over 8. And similarly, the fourth important t-coordinate that goes between 0 and 3 pi over 4, that's going to be 3 pi over 8. I'll let you verify that if you'd like by averaging 0 and 3 pi over 4, but it's almost the exact same calculation. And now we're set up to draw our graph. This is step 3, sketching the graph of minus tangent of, I believe it was 2/3 t plus 1. So normally what happens for a tangent function is it will start at this, well, of course we have these asymptotes, and for the 3 important t-coordinates that are not asymptotes, usually we start at the bottom, then go middle, then go top. However, since we have this reflection here, we'll start at the top, go middle, and then go bottom, as we mentioned previously. And we get this same sort of shape. It kind of curls in this way. So either you'll have a shape that looks like this, or you'll have a shape that is the reflection of it, which looks like this. And then finally, as we get towards the left asymptote, normally when you get towards the left asymptote, you would go to minus infinity. That is, you would plummet downwards. But since we have this negative again, this will cause it to go upwards. And as we get closer to the right asymptote, we plummet downwards for the same reason. Okay, and these are the details that I need for my tangent function. And this is where we're going to see asymptotes at x equals minus 3 pi over 4 and positive 3 pi over 4. So on my t-axis, if I choose a scaling, with this being pi over 4, then my asymptote would be here because this would be 3 pi over 4. And my second asymptote to the left would be here, minus 3 pi over 4. And I suppose we could just go ahead and draw those in. The most common way is with a dotted line. That, of course, is vertical. Now, in this particular example, you might be able to visually see where all the important t-coordinates are. So the third important t-coordinate happens halfway between minus 3 pi over 4 and 3 pi over 4, so it's going to be at 0. Then the second important t-coordinate is going to be halfway between minus 3 pi over 4 and 0, and maybe that one's not quite as obvious. If it's not, you can always go back to listing them out. So the third one is 0. Let's go ahead and check this. So this is the average between 3 pi over 4 and minus 3 pi over 4. So we add them up and divide by 2, and of course 3 pi over 4 minus 3 pi over 4 is 0. And then the second happens halfway between the first and the third. So negative 3 pi over 4, that's the first, plus 0 over 2, that's going to be negative 3 pi over 4 over 2, which is negative 3 pi over 8. Let's go over some terminologies for this trigonometric function, like we did when we talked about transformations of sine of t and cosine of t. Now, when we talked about sine of t and cosine of t, we had this term called amplitude, which essentially was the vertical stretch, but without any negatives. In this case, we don't use, in the case of tangent of t and cotangent of t as well, we don't use the terminology amplitude. That's reserved for sine of t and cosine of t. Instead, we'll call this the stretching factor. And it's simply, again, whatever is the vertical stretch, and don't include any negatives. So in this case, the stretching factor is just 1. While it's not common to see in most books, I do like to list what the midline is. And the midline is just going to be whatever the shift is here. So the shift here is +1. So the midline is y equals 1. The phase shift is whatever the horizontal shift is. In this case, there's no phase shift, but just to emphasize this point, the phase shift is obtained when you get the horizontal shift and this number is multiplying both t and the constant here. So in this case, the phase shift is just going to be 0. So the phase shift is the horizontal shift and in this case it's 0. And this is exactly the same as the definition for phase shift for sine of t and cosine of t. And then finally, the period is how long it takes for this graph to start repeating. The graph starts repeating after this asymptote, the second asymptote that we've drawn. So it is going to be this x value minus whatever this x value is. That's the first way to compute this. So 3 pi over 4 minus negative 3 pi over 4, which is 6 pi over 4, which is 3 pi over 2. There's a second way to compute this, much like the sine and cosine function, and that is you do the period of the parent and you divide that by whatever is multiplying the t. So in this case, that would be 2/3. So divided by 2/3. And now the parent, the period of the parent, in the case of sine of t and cosine of t, it was 2 pi. But in the case of tangent of t and cotangent of t, it's just pi. So this is pi divided by 2/3, so 3 pi over 2. Of course, you get the same answer in both cases, but just like in the case of sine of t, doing this computation doesn't require you to draw the graph. So if you just need to know the period, then you can do this computation. I think now that we've done this computation a few times, it's worth noting why this computation in this second part works. So what we're doing when we do pi divided by 2/3 is really we're doing pi times 3/2, which is in this problem and in every other problem going to be pi times the horizontal stretch / shrink. So we're multiplying pi by the stretch or shrink that's being applied to the parent function. So if your graph starts repeating for the parent function after, say, pi, then this repetition between these horizontal asymptotes is going to get stretched by this 3/2, and that's why this computation works. Instead of repeating after pi units, we're going to stretch that length of pi units by whatever the horizontal stretch is applied to the parent function. And that's exactly what's going on with the other trigonometric functions, the transformations of sine of t and cosine of t, except the old period wasn't pi as it is for tangent. Instead, it's 2 pi, and you're taking that 2 pi and you're stretching it or shrinking it by some amount. So just a little piece of information as to why this computation works. Finally, I'll make one last remark, which works both for tangent of t and sine of t and cosine of t. So here what I've drawn is the graph of one period of this function. But what if I wanted to draw more of it? In order to graph more of this, first you have to know what the period is. And the period for this graph is something we already computed, 3 pi over 2. So if you wanted to sketch another period, you would take all of these t values that you've computed and you would add 3 pi over 2 to them. Or perhaps a little bit easier, I think, you can take the asymptotes and add 3 pi over 2 to those. Note if you take the first asymptote and add 3 pi over 2 to it, you get the second asymptote, so this would move here. And then if you take 3 pi over 4 and add 3 pi over 2 to it, you have to get a common denominator, and you would get 3 plus 6, which is 9 pi over 4. And now remember, this is pi over 4, so 2 pi over 4, 3 pi over 4, 4, 5, 6, 7, 8, 9 pi over 4. And so my second asymptote would be at 9 pi over 4 here. So now I have my two asymptotes for the next period. Let's go ahead and fill in that this is 9 pi over 4. And then you can find the middle. So here, you can find these 2 points here, and those will be your important t-coordinates between 3 pi over 4 and 9 pi over 4, and then you just resketch the same y values. So there, and sketch again, and you get a copy of the graph that you had previously drawn, and that's it. I would say normally when one sketches trigonometric functions, they only sketch one period, but it is important to understand that though we only sketch one period, the graph of this function that we've sketched repeats over and over again. And so if you wanted to know the graph of this function, and it did not specify just one period, then you'd have to draw infinite copies of this graph in a way that I have just shown you here.